this competition business, okay? So, all right. So, we were here earlier, yeah? I told you about rho. And you didn't show it because it's kind of the same thing as the SI model, but we showed that the rho is the measure of the long-term fitness, okay? That's kind of what it is. Okay, so what I want to do is I want to introduce, at the within-host level, an explicit trade-off, okay? So the virus cannot just choose to increase K, increase rho, decrease mu, decrease C, right? Because you can't have any optimization in that situation, yeah? All that will happen is rho will get bigger and bigger and bigger and bigger. Okay, so what I want to do is introduce an explicit trade-off in the parameters, all right? So let me explain this. I'm going to introduce a trade-off between the amount of virus that can be produced, P, and the death rate of the cell. So what I'm going to say is, if P is big, then mu should be big. In other words, the virus cannot make tons of viruses from a cell without hurting the cell, which kind of makes sense, right? So let's put it slightly more biologically. If we've got cells and viruses, and they come together, and now we have a cell with a virus living in it, okay? All right, and the virus tries to replicate itself to make lots of viruses, okay? And then finally they get shed. So now we have viruses coming out, okay? So where does this hurt the cell? Okay, well, all cells have some background mortality, that's just assumed, yeah? But as the viruses are replicating, or as they're making more and more viruses, first of all, there's a direct cytopathic effect of replication. So it's not good to have a virus inside you using your cell resources just to make viruses, right? That's clearly a bad thing. So there's some direct injury to the cell. But possibly more importantly, there's an immune response to the cell, and that immune response will sometimes be much stronger when you're producing lots of viruses and shedding them, okay, than if you're just producing a small background quantity of virus. You may not actually have a strong immune response to that, okay? So this is these are the biological arguments as to why virus production would be correlated with cell death, okay? And it makes logical sense in just about any situation. If you have a parasite, that's not good for you, yeah? Nobody wants parasites, right? Okay. All right. Okay, so mathematically, how I introduce that trade-off is as follows. It's basically, I make the death rate be a function of the virus production rate. Okay, so the virus is producing at rate P, and then mu is some imposed function of that. Okay? So we're now in the realm of theoretical biology. Okay, this is theoretical biology, because I don't know what mu should be. Okay, I just don't know. All I really know is it should be increasing. Okay? But I want to impose some function mu as a function of the virus production rate P. It has an intercept at the background death rate. So in other words, if you're infected by a parasite that doesn't reproduce, then you just suffer background mortality. But as the virus reproduces more and more, you suffer more and more mortality. Okay? So that's the concept here. Okay. So, if we go back to the measure of viral fitness in the long-term measure, which is rho, it's now Kp over mu of P times C, okay? Yeah, so mu is now directly a function of P. And if mu is concave up, then the rho has a peak as a function of P. So we can say there's kind of an optimum for the virus in terms of its production rate. So it will pick, so basically there's a trade-off between lots of production, which is good for the virus, that's in the numerator of the fraction, and cell death, which is bad for the virus, which is in the denominator, okay? So basically you get a curve like this, and the virus in principle, under evolution, should select for this, this optimal virus production rate. Does it make sense? So you kind of expect the viruses to be around here, okay? Okay. Now, if we introduce the second strain, okay, so now the viruses get to choose So we have P1 for the first virus and P2 for the second virus, but they're both subject to the same constraints. Okay, so they both suffer from the same function here. All right? Okay, so this is now the model. So instead of just having a free choice of mu1 and mu2, what I have is I now have mu1 of P1 and mu2 of P2. Yeah. Okay, and if I run that model, okay, then I can choose a p-value so that the blue strain, you've already seen this one, right? But I can choose a p-value so that the blue strain maximizes the eigenvalue, the invasion speed, okay, which we already saw this is not exactly the eigenvalue, but you know, let's just let that slide for a little bit, okay? This maximizes the blue one, in fact, maximizes the eigenvalue at the beginning, but the red one maximizes the reproductive ratio. So the red one here could be the one that has the best possible value of the production rate, whereas the blue one is going too fast. Yeah, go ahead. It's a rate. I'm failing to see the problem here. You're worried about the dimensions? Yeah, dimensions are fine. Don't worry about dimensions, all right? They're fine. Just take it from me. All right, this P is a rate, mu is a rate, C is a rate, D is a rate. Okay, lambda is a number of cells, K is basically a rate per cell, so it's fine, okay? Yeah, this whole thing has dimensions of rate cubed or something like that, okay? All right, all right. So yeah, this is not dimensionally the correct thing for it to be an eigenvalue, but this is the correct mathematical quantity to think about, all right? Okay. Yeah. Okay, so now, so can we agree that, well, you should agree, that this model with these constraints, if I pick different values of P, I can get different kinds of curves here from different strains. Okay, so this is my within-host model. And then there's a very important thing. Now think about the between-host. Think about the epidemic. When you just get infected, suppose you just got infected, which strain are you most likely to transmit if you're infected with two strains? The blue strain. Way more likely to transmit the blue strain in the beginning. Right. What about the red strain? You would transmit that at the end. But what if you're already dead? Yeah? So you're seeing how this within-cell trade-off between production and death in the cell converts maybe into a trade-off between transmission and mortality at the higher level. Yeah? Yeah. So it's all fine to be the red strain, because you know you're going to win eventually, but actually the game already finished before you get to win. You know what I mean? Yeah? Yeah. Okay. All right. Okay. One little tweak on this that I'm going to use later on. Okay. Where do the different strains come from? Well, we could introduce a little mutation rate. Okay. So by introducing an epsilon here, the T1s, okay, can come about from V2s. So when a V2 infects a T cell, it can occasionally, with very small epsilon, it can create a T1 and vice versa. Okay, so we're assuming some kind of mutation between the strains. So epsilon is some tiny parameter. Okay? Okay. And we can extend this to n strains. I don't really want to go into this too much, but you could have a whole bunch of different strains. The one that invades first in the host would be the one with the highest eigenvalue, and then it would be replaced by the next one with the next highest eigenvalue, and then it would be replaced and so on and so forth until somehow the optimal one wins the whole game. Okay? So this is the most common strain, and it starts off with the strain which maximizes the eigenvalue, and then some intermediate strain invades that, and then some intermediate strain invades that, and then eventually you end up with the strain with the best value of rho. Okay, so you can kind of have this cascading effect, and it's kind of cool, and we wrote a paper about this. It's a lot of fun. This is 10 strains, and this is 100 strains. If you have 100 strains, everything gets really blurred out, so you can't really say so much, but you just kind of have this sort of cloud of viruses which is converging on being the sort of optimal long-term strain. You sort of get this sort of thing like this. And you can show mathematically that you get a jump from the fastest invading strain to one below it, and there's a gap here, and these strains never get to show up at all. So that was also fun. You can kind of show these sorts of things. Okay, so what we're going to do now is we're going to take within-host models of this type, and we're going to embed them inside an SI model. Okay, so we're going to take the within-host model and we're going to put it inside the epidemic model. Okay, as you should, right? Because now we've got trade-offs happening at different scales. We should try to combine these things together. Okay, so just as a reminder, here's my SI model. Okay, which is, I think, still on. No, it got erased, but it's that model. Okay, and here's the picture I showed you before of the virulence and transmissibility. And we kind of agreed that the fittest viruses were sort of up here, and the less fit ones were around here. Okay, so how are we going to link these two things together? So let's think about it. We've got a dynamic model for within-host dynamics, and we've got a dynamic model for the epidemic. That's a lot of dynamics, and they're not necessarily happening on the same timescales. So, what we did, first of all, was we ignored the within-host dynamics. Okay? We ignored the within-host dynamics, and also effectively ignored the between-host dynamics, and we just looked at what would happen at steady state. Okay? So we just looked at what would happen at steady state. Okay, so how do we do that? So what we did was we said, suppose the within-host dynamics have gone to equilibrium. Okay? So suppose that all of everything that's happening with, I just showed you with the lambdas and the everything, has gone to equilibrium. So we're only, so this is equivalent to supposing that the dynamics happen very fast. The big peak happens really quick. It doesn't really affect anything at the between-host scale. So we're only looking at the end game here. We suppose most of the transmissions come from the end game. Okay, so if we suppose that, then we can basically say that our within-host model is just supplying us with steady-state values of the parameters, of the variables. So we're always at steady state for t, t star, and v. Okay? So t steady state is this, t star steady state is this, n is just p over mu. Okay? I don't know why I wrote it like that. Okay? All right, so you've got your host, and your host is at steady state, and steady state basically means these values of t, t star, and v. All right? And you convert these you assume that the transmissibility only depends on these values, and the virulence only depends on these values. So the between-host transmission and death rates depend on t, t star, and v, and those are all at steady state for all patients. All right, so that basically means you can write your transmission as a function of the only thing which is really changing at the within-host level. We're just allowing the viruses to change p, okay? And you can write your virulence as a function of p as well, okay? So now we've got beta as a function of p and alpha as a function of p. P is determined at some microscopic level, but we're getting the transmission parameter and the virulence parameter are functions of that thing. And the way that that affects them is via the within-host variables, via the t, t star, and v, okay? Which we assume is at steady state. This is temporary. We're going to relax that, okay? So we'll come back to that in a minute. So what does that do? That draws a line on this phase plot. So here we have the virulence and we have the transmissibility. We know the virus wants to be up here, okay? But if we just vary p, what we find is p just goes like this. Okay, so how did I get this curve? Well, I had to specify specific functions of beta and alpha. So here, I just said, let them be linear functions. So the transmission is just a function of the viral load. It's just a linear function of the viral load. And the virulence is a linear decreasing function of the T cells. So as you lose your T cells, you might get more sick. That's just the idea, right? Okay, so beta is this linear function, alpha is this linear function, and if we can, as we range over different values of P, we basically build this curve here. So different values of P are converted into this curve here. So where should the virus choose to be? Right. So I'm just telling you, you can't see it on this plot, but the best possible value of P is in the red where the red circle is, okay, at the within host scale. So the competition within host would be expected to favor viruses which have this p-value, okay? And the between host scale, well, we can actually see that. Which point on this line corresponds to the highest fitness? It's also this point, okay? So this is, this is low fitness, gradually increasing at the between host scale. So the best point is the black one. So if everything's at steady state and you choose beta and alpha to be those functions, there is no conflict between how you would want to be at the within host level and how you would want to be at the between host level. So we would expect, since all of the selection pressure, since all of the optimization the virus can do puts it in the same place, that we would end up here. Okay, but those functions are kind of arbitrary, yeah? Like, why would we think it would be linear? Well, it might be, but it might not be, okay? So what if we chose some different function? So let's take the transmission to be a increasing concave up function, say a power function of the viral load. So in other words, having a higher viral load really helps you, yeah, in terms of transmission. And let's say that the virulence is a somewhat stronger function of the loss of T cells. So you can see there's a 1 over T there. So at some point, if T gets close to some minimal value, T0, you get a really strong virulence effect. Okay, so why not? This could be the case, right? If the virus takes a lot of cells, that could be a problem. So if you use those functions, and then you vary P in the within host model, and carry them through through those functions, then you get this curve. Okay? And what happens here is you get very different information. Okay? So the within host optimum turns out to be for some p-value that's up here. But the between host optimum turns out to be some p-value that's over here. Okay? So what's really interesting now is you have selection at the between host level trying to push you to one place. Yeah? So it's trying to push you over here where you're not very virulent. So the patient lives for a long time. They get lots of transmissions in that time. But selection at the within host level is trying to push you over here, which is clearly much worse for the patient because you have a very high virulence. Yeah? Does that make sense? Yeah. So depending on what those functions actually look like, you would predict sometimes the selection would all be kind of pushing the virus to a particular choice of parameters, as it were, and sometimes it's not. It's pushing the between host selection and the within host selection can be pointing in very different directions, as it were. Yeah, well, I don't even know those points are stable. So suppose you have a virus here, as soon as you put it into a host, if it generates a few mutants, they're most likely going to be going this way, back towards this optimum over here. On the other hand, if you take a virus over here, and then in its ecosystem of hosts, introduce a virus over here, this guy's going to invade, this guy's going to do a better job, right, generally speaking, of invading. So it's clear that this is quite complicated. So this was a whole paper of work. So we just basically, all we wanted to show was if you have a within-host model and you introduce it into a between-host model, and making a few assumptions to make things sort of clean, you can get really confusing. You don't really make predictions. All you have is, well, things could be in conflict. You have different selection pressures acting at different scales on the virus. And we didn't really have, we still don't really have a resolution for that. Okay. So, yeah, go ahead. No, we really tried not to look at data for this. This is theoretical biology, okay? So we were just trying to get a sense of what's the potential universe of models out there? What kind of predictions might those models make? The only thing I would say is I think that the transmission function beta should be an increasing function of V. I don't see why your transmission would get worse if you have more viruses. That just seems weird. And I would also think that the death function alpha would be a increasing function of T, possibly T star, don't know, yeah? It will be an increasing function of T because having target cells is presumably good for the host because, well, we have them, right? And the virus is taking them away, you know? So this is true theoretical biology. I mean, there's no real parameter estimation going on here. We're just trying to figure out what would happen in this kind of model if we try to put these models together. Okay. So, yeah, so just to summarize, selective pressures on viruses from the between and the within host levels, they can conflict. And then it's not really clear what the virus should do, you know, what you would expect to happen. But this analysis does not say very much. So you'll notice I ignored something. You know, I made a big deal earlier on about telling you about the blue strain and the red strain being the long-term competitor and the blue strain being the early competitor. So we sort of ignored that, yeah? Because we just said, let's let the host go to steady state. So the red competitor would always be the winner, in a sense. Okay, so what we did next, okay, and the results get even more equivocal in a sense, okay, but we said, okay, let's deal with that properly. Let's take the dynamic within host model and embed it into an SI model, okay, so we basically did that, okay. So what we're doing is we're considering competition between two strains of a chronic virus with different P values, intracellular production rates, so the P in the intrahost model, across a population of identical hosts. So there's no structure in the epidemic model. It's just a bunch of hosts. Okay, and each host could be uninfected, or it could be infected just with strain 1, or it could be infected with strain 1, just with strain 2, sorry, or it could be infected with both strains. Okay, so we're allowing for co-infection. So when you get infected, so if I come along and infect you, if I have strain 1 and strain 2, I will give you strain 1 and strain 2. Okay? So that's how it works. So if strain 1 is really better than strain 2, it should be able to somehow beat out strain 2 in that scenario, and you'll be left with just strain 1 in the population, or vice versa. Okay?
Mutation that appears.
I'll get to it, all right? Because there's different assumptions you can make there, yeah. Okay. But we don't allow for superinfection. So superinfection is when you're already infected with strain 1. So I'm sitting here and just feeling a bit poorly with strain 1. And then a couple of weeks later, someone comes and sneezes and I get strain 2. And then we're not allowing for that. Okay, because that gets really complicated because then you have to structure it by the time at which you get superinfected, and it's a big mess. Okay, so we don't really have that. Okay, so this is a co-infection model, not a superinfection model. Okay, so here's a schematic of what's going on. So this guy's not happy because he's sick. Okay, but anyway, age 0, age here means age of infection. So how long have you been infected? So when this guy just got infected, so his age of infection, A, was equal to 0, he received some viruses, okay? That could be strain 1 or strain 2 or a mixture of both, okay? And so now within him, we run the within host model, okay? We run the within host model within this guy, okay? And we're really interested in knowing how long has he been infected, how many T cells does he have, because that's going to govern his death rate, and how many V1s does he have and how many V2s does he have in his body, okay? Because that's going to control the infection rate to the next host, okay? And then you see the beta there is the transmissibility, and so his transmission is going to depend on how many viruses he has. Okay, so he's going to transmit according to how many viruses he has. Okay, and so then he proceeds to infect 3 other guys, and they each have their own infection dynamics going on. All right? All right. He may also die, and that death rate could depend on how long has he been sick for, and or how many T cells does he have left. Okay, so we could imagine it could depend on a number of things there. Okay, so the thing I haven't specified here is what's going on here. So he gets infected, and that sets initial conditions for this system. So what he gets infected with is really important, okay? So the rule that we decided to follow was the following. If I have only strain 1 and I infect you, then you will only get strain 1. If I have only strain 2 and I infect you, you will only get strain 2. However, if I have 80% strain 1 and 20% strain 2, then you will get 80% strain 1 and 20% strain 2, okay? So I can infect you with both of them in proportion to how much I have, okay? So a schematic of that looks like this. So this is strain 1 on this axis within me, and this is strain 2 on this axis within me. And basically, I got infected somewhere. Actually, where did I get infected? Yeah, I got infected here. And you see strain 2 did really well. That's like the blue strain. So the blue strain did really well for a while. And then as I was infected for longer and longer, strain 1 came up until eventually I end up at like the steady state because strain 1 excludes strain 2 after a while. Now suppose I infect somebody when I'm here. Then basically I draw a line back to the origin and I infect with this much. I infect with in these proportions, this much strain 2 and this much strain 1. Okay? Suppose I infect somebody at this point. I draw a line back to the origin and I infect roughly 50-50 strain 1, strain 2. And if I infect somebody over here, then it's mostly strain 1 and less strain 2. Until if I'm infecting people from over here, then I don't transmit any strain 2 at all. Okay? Does that make sense? So that's the rule. And this line here kind of tells me how big is the initial packet of virus that I infect somebody with. Yeah, so it's like 100 viruses or something. So in this case, it would be 50 V1s and 50 V2s, and in this case, it would be 80 V1s and 20 V2s, something like that. Okay. So you can do this, okay? And basically, this is a very complicated graph. You can consider two cases, whether you have mutation or you don't have mutation. And I'm plotting here, this is the proportion of V1s in what you're transmitting. So if you're down here, you're transmitting 0 V1s and all V2s, and if you're at the top, you're transmitting V2s and no V1s. Okay? If there's no mutation, then basically, if you get infected with some inoculum containing variable amount of V1s and V2s, then unless you're infected only with V1s, the V2 will win for a long period, so you'll be only transmitting V2s until eventually the V1 comes up, okay? And these different lines represent different initial conditions, okay? So this is 80% V1, this is 20% V1, okay? So we have this. And this is just a zoom in of what's going on at the beginning. So basically what's going on at the beginning is the V2s are beating them out, okay? Alternatively, you can also allow mutation. And at that point, even if you're infected only with strain 1, strain 2 will come in and win after a short period, okay? And then strain 1 will come back again, okay? So you get a little bit of a softer response there. Okay, so then how do you decide which strain wins overall? So this is just telling you about the transmissions from different patients. Okay, it's complicated, but you can do it. So what you do is you basically look at this as an integral, a system of integral equations, okay, where the transmission is integrated across all ages of infection, weighted by the transmissibility. Now, I appreciate you don't get this, that's fine, okay? But basically, you sum up all of the transmissions a person makes when they're infected with some initial inoculum, and then you pass that forward to the next generation, and it turns out to be an integral over some space, okay? If you want to read the paper, I can point you to it. Yeah? Not the calendar age, only how long they've been infected. Oh. Yeah. That would, but do you really want me to introduce another dimension right now? I'm having enough trouble explaining this as it is. But basically, this thing ends up looking like a linear integral operator, and you figure out the biggest eigenvalue of that integral operator, and that biggest eigenvalue tells you the rate of spread into the population, and the eigenvector associated with that eigenvalue tells you the distribution of strain 1 and strain 2 that you'll achieve in the population at steady state. So you can basically say which strain wins, including the within-host model and the between-host model. All right. I fully don't expect anyone to follow what I just said, okay? But there's a way you can do it, and it's kind of semi-analytical. So again, you solve some differential equations, you do some integration, you kind of get a solution. So I can specify how I do it, and I can do it to high precision. If you don't like my model, well, that's your problem. For my model, I can do it to high precision. Just reminder of the within host. Okay, and then basically, that should have been blue, sorry, but okay. So the blue strain or the yellow strain, sorry, that I got mixed up here. The blue strain is the same as the yellow strain. The red strain is the red strain, okay? And what we're interested in here is we're supposing that the red strain is the within-host, the optimal within-host competitor, and he gets to compete against another strain with an arbitrary value of p. So p is the within-host parameter p, and basically there is a range here where the second strain is close to, but not exactly the same as the first strain, and it's able to win the competition among hosts and dominate completely the competition. Basically, it's when the blue strain is kind of similar to the red strain, but it's just a little bit faster at the beginning, so it gets the whole benefit of this area, and then eventually it gets replaced by this one, okay? So for these strains here, which are the strain 1 is this guy. The strain 2, if it's close to, but not, if it's close to the first strain, then it's able to beat it completely in the population. This is the no mutation case. If you introduce the mutation case, then actually you can get a regime where there's coexistence. So you will end up with both strains present. So basically what's going on is it's very hard to completely outcompete the other strain because you're constantly producing it through mutation. Yeah, so I would interpret this as just very low levels of strain 2. Okay, and you get interesting things where there's a region here where strain 2 can exist, can beat out strain 1 completely, but then you just move a little bit and strain 1 is winning again, and then you move a little bit and strain 2 is winning, and then you find this region where strains 1 and 2 will coexist in the population, okay? And what's generally going on here is you get infected with some mix of strain 1 and 2. Strain 2 kind of wins the early game, and strain 1 wins the late game, but these effects kind of balance each other out. So yeah, and I don't want to go into this at all, but we tried this with 5 strains as well, and we got graphs like this. And it gets harder and harder to interpret. Yeah, okay, all right, let's skip that, okay? So, what I did was I presented ways to combine the within-host and the epidemic scale models together, and I think the results are fine, and I stand behind the results for these models. I don't know if those are the models I would necessarily want to use for any particular disease if I had actual data, yeah? But the thing that I think is interesting here is the process, and the way that it brought into focus for me and my collaborators, what did we need to think about to do this? So it's basically fairly simple. The recipe is 4 things, okay? So you need your within-host model. And that within-host model has to be, you have to believe it for competition between 2 strains within host. So if you believe your within-host model for competition for 2 strains within host, then, okay, check, we have a within-host model. Okay. Then we need transmission functions. So how do the variables of the within-host model impact on the transmission between hosts? So there's a guy in Georgia called Andreas Handel, and he thought about this, and he came up with some functions for his model, and he calls them the snot functions. So basically it's do you know what snot is? Yeah, it's the amount of snot, it's what comes out of your nose when you have a cold. Okay, so he basically takes the viral load and he computes an amount of snot that comes out. And it's fit to data from ferrets, where they actually can measure these things. And then he uses that as kind of a transmission function for his between-host model. Anyway, so you need some kind of transmission function. So how does the viral load, how does the T-cell state, how do those kind of things affect the transmission to the next host? Okay? Then you need an understanding of what initial conditions do you place in your within-host model. So what gets transmitted? How many viruses? What's the mixture between different strains if there's multiple strains in the transmitting host? Does that make sense? Yeah? So you need to think about that. No one knows how many viruses get transmitted basically for any disease. There's one founder strain. So how many viruses there are, no one knows how many viruses. It does look like for 70% of HIV patients that whatever came in was genetically identical. However, once the cell's infected with HIV and it's producing the viruses, they're basically all exactly the same. The mutations happen before the cell decides what to produce. Does that make sense? Yeah. So those statements are not incompatible. Okay. Also, there's 30 or so % of HIV patients which appear to have been infected by multiple founders. So that would also indicate there's more than one virus. Yeah. Okay. But anyway, you need to have an idea about how you want your initial conditions to go. And then you need an epidemic model. So here we just used SI, which is the most basic epidemic model there is. And if you've read the epidemic literature at all, you'll know that there are epidemic models which take into account ages and even sexes and different locations, different immune states, vaccination. You know, all of the world of epidemic models can be included at this point. Yeah, you're going to make things very complicated, but you can do it. Okay? So these are the 4 things that you need for your recipe. And you know, I would say in order of how well developed they are, there's lots of epidemic models, and people have quite a lot of confidence in epidemic models. There's a reasonable number of models of virus dynamics. What's missing is really a good understanding of these 2 pieces. There's still not very much in the literature about how you do this kind of thing. Okay. All right. Okay. I'm assuming the slides get put on the web, so here are some references to my work, because you don't need to write them down. These will go on the web. Okay. We like to think these are good papers, but you know, other people may disagree. Okay. I still have a little bit of time, so I wanted to do one more thing today. I just wanted to show a new project that I've been working on with a grad student at home. Is that okay with you guys? Okay, so this is in the lines of immunoepidemics. It's not finished. Okay, so first of all, don't steal our ideas. And second of all, I think I can trust you. And second of all, I don't think this is finished. And in fact, at the end, you guys should feel free to criticize. I'm interested to hear what you think. Okay? All right. So I just want to kind of sketch out what we're up to. So we're interested in looking at drug resistance evolution in a simple influenza model. Okay, so influenza for most of us is not much fun, but you know, you lay on the floor for 3 days and then you get back up, right? Yeah? Does that summarize? I don't know. Some people have serious complications though from influenza. So in particular, elderly people have a much higher mortality rate from influenza than the general population. Or you can have people who have conditions that mean that influenza can be much more serious. Okay. So what can you do if you have an elderly person who has influenza? Yeah, you can't vaccinate them if they're already infected. That doesn't work. So what you can do though is you can offer them antiviral treatment. So Tamiflu is the trade name of one of these antiviral treatments. Okay, so you can offer this. But it is well known, so for example in the United States, about 10 years ago there was some pretty good data indicating that Tamiflu resistance was appearing in the circulating strain of influenza at that point. Yeah, so drug resistance can come up during an epidemic. Okay, so we're interested in this. So what we did was we developed a combined within and between host model. Okay, the between host model again is very, very simple. Okay, and I'll show you how we do it. And the within host model is not so different from this. Okay, but rather than having multiple strains of the virus, what we have is we have treatment. So treatment comes in, and then we can have, we do have multiple strains of the virus, but we start off with a wild-type virus, and then when treating, it can lead to the selection of a drug-resistant virus within the host. Okay? All right? And then I don't have many results, because this is an ongoing project, but we're interested in looking at how timing of the antiviral treatment might be important. Okay? So, in other words, treating patients early with the antiviral, say after 12 hours of infection, or 24 hours of infection, or 36 hours of infection, or things like this. Okay. So, here's our within-host model. Okay. So, the X at the top, the chi at the top is the healthy cells. I'm not going to give, actually I will show you equations, but the chi is the healthy cells, okay? And the Y's here, okay, are infected cells that are producing virus. We don't model the virus explicitly. We just allow, for instance, this is Y, this is a cell infected with the susceptible strain of the virus, and it just directly interacts with an X, and it makes an LS. L is a latently infected cell. So it's a cell that's become infected, but is not currently producing virus, and there'll be a delay before it produces virus. Okay? So this is actually what happens. The virus gets into a cell, then there's a delay of a few hours, and then the virus begins to be produced. So L is modeling that. Okay? The sub S here means susceptible. So that actually means the virus is susceptible to the drug. Okay? So this is a cell which is infected but not yet producing viruses, and it's been infected with the drug-sensitive strain. Okay. So it produces now drug-sensitive infected cells which are producing virus. Okay? And we don't model the viruses. So this cell just interacts with the healthy cells and produces more of these guys. Okay? Yeah. So we decided we weren't going to include explicit virus in the model. Yeah? So I just keep going? You probably want to know about what the R stands for, right? Yeah. So the R is drug resistant. So this is a cell, these are cells infected with drug resistant virus. Okay? So the drug resistant strain of infected cell is here. Okay? All right. Okay. And you probably want to know what U is. You want to know what U is? Okay, so the difference, well, one of the important things about flu infection is that the immune system clears it. So we made I'm going to say a model of the immune system. U is the strength of the immune system, and basically at time 0, U is very low, and then it grows. Okay? And the U here, and I'll show you in the equations on the next slide, the amount of immune system there is impacts on the reproduction of the virus. Okay? All right. And then there are lightning bolts. Do you want to know what those are? That's when the god Thor comes and throws down. No. Actually, it's Zeus, isn't it, that throws the lightning? But the lightning bolts are the things which are infected by the drug. So if you have a patient and you affect them with the drug, you hit them with the drug, it's going to impact on the ability of the cells to produce new infected cells. Okay, so here's the drug here. This line here is the mutation. Okay, so this is mutation. So this cell here is going to mutate, and it's going to produce viruses that are going to lead to a resistant strain. Okay? So patients in our model ultimately can be infected with a resistant strain as well as infected with a susceptible strain, but within a patient who is has drug-susceptible virus, they also have the possibility of generating mutants. Okay? And that can happen before the drug is present or after the drug is present. Okay. All right. But it's very rare. It's very rare. And now I'm going to give you a quick test. What kind of model should you use if you have rare events? Stochastic. Okay. So we code this up. We coded this model up as Gillespie in a Gillespie simulation framework, just like you guys did yesterday. All right. And then, so my student, Judith, she gets her laptop and she press return. We put in some parameter values that we like. You know, so like good parameter values that we think are to do with flu infection. You know, we tried to do a good job on the parameter estimation. It's a sketch model, but you know, do the best you can. She hits return, and then it takes forever. It takes forever to run because there's actually quite a lot of cells. Okay, and so the Gillespie is constantly going up and down in the number of cells. You know, you saw how Gillespie is working, right? It can be quite slow. So one option would have been to find a better computer, but instead what we did was we actually decided we were going to build a combined stochastic differential equation solver. So for the rare events, it's run through the stochastics. For the frequent events, it's run through differential equations. Okay, and so we basically have a combined tool for doing that now. Okay, which I'm not going to talk about, but it was interesting. Yes?
Have you coupled it?
We have a threshold level. So once the stochastic thing hits the threshold, we switch it over to the appropriate differential equation from that point on. Okay? Yeah?
What are the doublers?
Oh, here?
Yeah, well, on the right.
Oh, this?
Yeah.
That's stuff dying.
Okay,
But
you have two errors. So for white, we have two lines going down.
oh, I have no idea. Hold on, let's get the equations up and see if we can explain that one. But yeah, was there a question? Can I show you the equations? Yeah, can I show you the equations? And we'll see where U comes in, all right? I think it might answer it.
I'm wondering if these two lines here is natural cell death and
It could be.
cell death in response to the drug.
Hold on. It could be. I think it's just a mistake, actually. This figure is adapted from another figure and so on and so forth. So yeah, anyway. All right, so here are our equations. And I just want to draw attention to the mu here, okay? To the mu. Sorry, U. So U is the immune system. This 10,000, I intentionally left this here just to make it clear that the immune model is completely made up, all right? So we just made up a model, okay? So you can see this is logistic growth of some immune presence, okay? And that I intentionally made it look like it was weird, so I put 10,000 there, because you've got 10,000 here. And you can see what the U does. The U will kill off the infected cells that are producing virus. It doesn't touch the latently infected cells, it kills off these guys, okay? We have mutation of form epsilon, okay? That you can see the mutation term there, which is switching from drug sensitive to drug resistant. Okay. All right. Does that make sense? And I don't have a plot of this, but if you just run this model, basically you get a nice curve. Okay. So this is the best you're going to get. I don't have a plot of this model running, but basically, even allowing for the stochasticity, it kind of starts off a little wobbly because of the stochasticity, and then it becomes kind of smooth. You get a nice viral peak. It comes down. Now, in the HIV model, it levels off, right? But because we have this immune term here, which has been growing to represent the increase of the immune system during the infection, when it starts coming down, it just comes down and goes to 0. Okay, so basically it goes whoomp. All right, so the virus load does this. And that's actually very representative of what happens in flu infection. Okay, so we're fairly happy about that. Okay. All right, so one thing we can do is we can look at the emergence of resistance in the emergence of resistance when you run the simulation. Okay, so I just want to tell you, if you don't apply the drug, then you get no resistance, because we set the parameters so that the resistant strain is slightly weaker than the wild type strain. Okay, so it won't come up, the resistant strain will not come up in the absence of drug treatment, okay? But if you apply the drug treatment, then you can find that as a function of when you start treating, so you apply the treatment and it stays on forever after that, okay? If you apply the treatment too late, then there really aren't that many viruses being produced anymore, okay? So there's not an opportunity for that rare mutation to happen. So basically, if you treat late, you don't see any thing. On the other hand, you probably haven't helped the patient very much if you treat late, because they had to go through the worst part of the disease. Okay. If you treat really early, we didn't really consider much earlier than this because we thought it was unrealistic that somebody would get treated that quickly. But if you treat super early, then you also don't get resistance, right? Because you kill off many viruses. And basically, the patient never goes through this. The patient just kind of goes like that. The virus load goes down very rapidly at the beginning. And again, there's not much opportunity for that rare mutation to happen because the replication has really been switched off. Yeah? So the time when you get the resistance emergence is if you treat for an intermediate length of time. Okay? So, sorry, if you treat after an intermediate length of time. So if you treat after about a day, you get quite frequently out of 1,000 of our simulations, it's stochastic, so it's different every time. So we do 1,000 runs, we get about 50 times with these parameters. We get about 50 times when you'll see the resistant virus come up. Okay? All right. Okay. So we embed this now into the between host model. So here's the between host model. So we have susceptibles. We have individuals who are infected with the resistant strain. So they were infected with the resistant strain at the beginning, and we know what they do. We know how the virus goes in them. We can run the within host model. We have individuals infected with the susceptible strain, okay? And then some of those get treated. All right, and these are the ones that are going to generate the drug resistance to begin with. So the initial start of the model is dominated by S and IS, and then the S's eventually become recovered. Yeah, but after a while, if you apply the treatment, you start to see, well, obviously these people will be in the model, so this starts to come up, and then as soon as you start treating, especially if you're treating at 25 hours, as I showed you, you'll start to generate people so the resistance will come up in these people, and then you'll have these people showing up as a result, and then this group can self-sustain a little bit, especially if you keep treating. Make sense? So that's kind of how the between host bit goes, okay? And then how do we link them together? What are the other pieces of the recipe here? Okay, so the total transmission is, so what we actually do is we run the full within host dynamics all the way through, and then we integrate out a total infected cell load, which is supposed to be like a proxy for the viral load. Okay, so we just integrate this. Oh, that should be over T, sorry. We integrate over T, so we get the summation of sort of the intensity of the infection. Okay, and then we put it into a completely made up function to convert it into how many new infections are there. So you could call that an R0. Okay, so how many people get infected by this person? So we take this quantity here, call it X, put it into some sort of Hill function, and we get an R0 from that. Okay? Again, I leave the numbers in here just to emphasize that we're just coming up with something. Future work, by the way, is to sort of improve this part by looking at animal transmission models. So people who infect ferrets with the flu and try to figure out how frequently they infect each other. Okay. Okay, and as I said before for the previous model I was describing, the transmission of the different strains occurs proportional to how much they are in the transmitting patient. Okay, so you can be infected in this model with a mix of strains again. Okay, so then we run this. Okay, we run the epidemic model, and each person who's infected gets to have their own within host dynamics, which includes treatment. Okay, so we run this, it's very stochastic here. You have a stochastic epidemic model. Within that, you have a stochastic within host model. And we can get results like this. So for example, looking at the final size of the epidemic. So there are 1,000 people in our simulation. Okay? How many people get infected by the end of the epidemic? Okay? And how does that change as a function of the treatment time? Okay? So basically, if you treat super late, as we saw, it doesn't really have any effect on anything. So this is essentially what would happen if you never treated. If you treat early, you can reduce the size of your epidemic. That makes sense, right? So if you treat everybody early on, then you get a much smaller epidemic than if you treat, I mean, this is almost the same as not treating, because the people have already done all their transmitting by this point. Okay? Sorry? No, this is the recovered. Oh yeah. Total sensitive plus resistant. Yeah, absolutely. Yeah, so you can see that drug treatment does actually improve matters in terms of reducing the final size, especially if you do it early. However, that's at a cost, right? And the cost is maybe introducing drug resistance. Okay, so if you look at the drug resistance, it's actually extremely variable. Okay, so this is the fraction of cases during the whole epidemic where the patient was not helped essentially by the drugs because they had the drug-resistant strain. Okay, according to the treatment time. So again, you see, if you treat early or you treat late, the drug doesn't really do anything in terms of producing resistance. Okay, so because you're treating so early here, there's no opportunity for resistance to come up. I mean, you can see occasionally it does in a small number of the runs, which is kind of interesting. Not so much over here. But for the middle here, on the whole, there's not very much resistance that comes up. However, in some fraction of the simulations that we ran, we get a pretty significant amount of up to 100% of drug resistance by the end. Okay, so this is kind of interesting. All right, that's where we're at with the project. I don't really have much else to say about that. I just thought you guys might enjoy it. But so what we can do with this model is we can estimate the rate of generation of drug resistance and then the transmission and spread of the drug resistance. It's work in progress. And here and there I'm saying things like, this is a completely made up function, right? And one of the things we're working on is trying to improve that part. The other direction that we're going in is, so right now we have one population, they're all susceptibles. We want to work on having elderly people and maybe healthcare workers. So if you have an old people's home, right? And you have the healthcare workers they would follow somewhat different dynamics than the elderly individuals in the home. And the elderly people would be at a higher risk of death due to having an untreated infection. So we can also sort of, in some sort of ballpark way, convert this into mortality during the epidemic for the elderly people. Okay, so that's kind of the longer term goal for this project. Anyway, mostly we're doing it because it's fun, I have to say. Yeah, go ahead. Yeah, you have to be a little bit careful, but yeah, you could do this for a number of other acute infections. Yeah, I mean, anything where you have a antiviral that you could have resistance evolving to, you could do something similar to this. Yeah. We're not the only people to work on this, all right? If you look in the literature, you will find other papers in this sort of general vein. Yeah, this is just my attempt with a student to do something interesting. Yeah. A less fit. Yeah, arguably, yeah, it could be, yeah. So the question was, if we make all the viruses be drug resistant, they should be less fit in general. So we've actually improved matters. Yeah, it depends on sort of what's the link between viral fitness and human mortality would be a question, right? Yeah. Anyway, okay. Any questions?